and welcome to another WJEC A level physics question. This was question 6 on the June 2015 Unit 5 paper. This is about the Hall effect, which is nowadays in Unit 4. So what we've got in the first part of the question is electrons flowing through a semiconductor slice that's being used as a Hall probe, and we've got various bits of data on the questions. And first of all, we've got to indicate on the diagram the face of the slice that becomes positively charged. So what we've got here is electrons are flowing from the back of the page to the front of the page. And remember that the direction of a current is the direction in which positive charges flow. So we can consider the electrons coming towards us as being equivalent to a current away from us. So what we're going to do is we're going to use Fleming's left-hand rule. We're going to point our first finger for the magnetic field downwards. You're going to point your center finger away from you to represent the current, and you should find that your thumb points from left to right. So there's going to be an electric force in this direction on the electrons. So that means that the electrons will be pushed to this left-hand face, and that means that the right-hand face will be lacking electrons, so the right-hand face will become positively charged as required. To connect a voltmeter to measure the Hall PD, you just need to connect it between the two faces, the positive face and the opposite face that will become negatively charged. To calculate the Hall voltage, what we've got to realise here is that there's a balancing between electric and magnetic forces here. The magnetic force on the electrons is BeV. The electric force on the electrons is the electric field set up between the two opposite faces of our semiconductor chip times the charge of the electron. But we can also remember that E is equal to V over D. The field strength between a pair of plates, this is like a capacitor, is the potential difference between the plates divided by the separation of them, and the potential difference between the plates is VH. So if we put everything together here, well, first of all, let's cancel an E at this part of the equation. We'd have BV is VH over D, leading to VH, the Hall voltage being BVD. You can simply quote that formula, but you won't find it in the data books. The magnetic field strength is 0.22 Teslas. Speed of the electrons in the question is 5.7 times 10 to the minus 3. And D here is the distance between the two faces that become oppositely charged, so it's the 5 millimeters. We put those figures into the calculator. You will end up with 6.27 times 10 to the minus 6 volts, or 6.27 microvolts. Next, we're asked to explain why no work is done on the electrons as they move through the slice, the slice, why no work is done by the Hall voltage. Well, remember what we basically said is we've got two forces. That's the magnetic force, sorry. We've got the magnetic force and the electric force acting on the electrons in opposite directions. Eventually they balance. The electrons will move straight down the center of our slice, and therefore the electrons don't move in the direction of the Hall voltage or the electric field. And since work done is force times distance moved in the direction of the force, if we're not moving in the direction of the Hall voltage or the electric field, there's no work done. So we're just going to say here that there is no movement in the direction, or no movement of the electrons in the direction of the electric field. And the direction of the electric field is basically the same as the Hall voltage. For the final part of the question, we're given a concentration of free electrons in the semiconductor slice of 7 times 10 to the 22 per meter cubed. And we've got to calculate the current in the slice. So we're going back to AS physics with the I equals NAVE formula. N is the free electron density, which is that 7 times 10 to the 22. Now A is the area of the face through which the electrons are moving, so it's the area of this front face, which is 0.95 millimeters by 5 millimeters. And again, make sure we turn millimeters into meters. V is the speed of the electrons, which we were given in the part B of the question, 5.7 times 10 to the minus 3. and E is the electron charge, 1.6 times 10 to the minus 19 coulombs. If we put all those into the calculator, we end up with an answer of 3.03 times 10 to the minus 4 volts. Amps, because it's a current that we're finding. So thank you for listening. Please remember to like and subscribe, and feel free to ask any questions. Goodbye.